All right, it's 3:30, so let's get started. Thank you everyone for coming to the TAP Colloquium and also to the poster session for the Time Step program. So in today's colloquium, I'm really excited to introduce Professor Edwin Kite. Edwin completed his undergraduate at the University of Cambridge and his PhD at Berkeley in the Earth and Planetary Sciences Department. He then had prize postdoctoral fellowships, the Earl Fellowship at Caltech, followed by the Hess Fellowship at Princeton. Since then, he's been a professor at the University of Chicago, where he's done a lot of pioneering work on Mars, in particular the Mars climate problem. How do you reconcile evidence for past fluvial activity with climate predictions of cold climates, as well as on the nature and evolution of small exoplanets, the so-called sub-Neptune exoplanets. Edwin has a number of prominent honors. For example, he's won the Really Early Career Award for Planetary Science, as well as the AAAS Newcomb Cleveland Prize. He's a participating scientist in MSL and involved with a number of JWST observation programs. And currently, he's a fellow at the Astera Institute, working on the question of Mars terraforming, which is, I believe, the topic of today's colloquium. So Edwin, thank you so much for coming out. Please take it away.
Thank you very much, Sukrit. Thank you for the introduction, and thank you for the invitation. Please interrupt at any time with any question. You don't have to wait to the end if it's a burning question. This is an artist's impression of the near future of Mars that we could enable. But it could be a vision of our own planet about halfway through Earth's history, on the cusp of the great oxygenation event, and after oxygen-producing microbes have established themselves on our planet. So this is the heart of the problem of Mars terraforming: how to compress the planetary development that has made at least one world habitable to us, that took billions of years, and accelerate it to timescales that are relevant to our society, our civilization. So when can we do this? The key is a warm climate enabling first small amounts of liquid water and then rivers and lakes. We're zooming in on the fastest volcanic province in this artist's impression. There are snow-capped volcanoes off to the left, and the extent of water is set in this model, assuming the ice caps melt with basically no extra water, which gives a relatively dry planet. So how can we make Mars a green planet that can sustain a biosphere? This is a very big scientific research area, and I'm only going to touch on part of it today. It involves much more than the warming step. So I'd especially thank the lead authors of the papers I'm going to be surveying today, especially Mark Richardson, who might be here. Hi, Mark. And also Samantha Ansari, who led our pilot study, and Erica DeBenectis, who led our Nature Story paper that should be out next month. And so these partnerships will allow us to cover a lot more ground than we will learn. So if we're going to reach the stars, we will have to maintain a common purpose over hundreds of years. And one thing we all have in common is Earth. As far as we know, the only planet with a sunlit ocean and an atmosphere we can breathe. So for the foreseeable future, Earth will be where almost everyone will live, our only homeworld. So we all live on the greatest planet in the universe. I don't want that to always be the case, however. So our ancestors were, to paraphrase Darwin, hairy tree dwellers. And they moved outwards and built tools like spacesuits and clothes to cope with once unimaginable hazards like winter snow and vacuum. But this approach of adapting ourselves to the environment can only take us so far. Throughout time, space has been forbidding to life with radiation, micrometeorites, and extreme cold. So if we're going to have an adventure that extends to the stars, we'll need to adapt the environment to ourselves. I don't know for sure how we'll do this, but the bigger and rocky icy worlds of our own solar system seem like a logical place to start. Many are rich in the life-essential volatile elements, all can offer radiation protection, all have enough gravity to hold on to a stable atmosphere. So if we decide in the future to bring life to other worlds, enlarging our environmental responsibilities, it's agreed that warming Mars will be the first step in making Mars's surface suitable for life. Work on this runs from the pioneering ideas of Carl Sagan and Chris McKay through new ideas like aerogel warming, solar sail mirrors, and engineered aerosol warming. So why terraform? Why turn a dead planet into a living one? So for any level of technology, 2 planets have more carrying capacity than 1. So terraforming allows us to expand our numbers. For many, terraforming offers some protection for our biosphere, our consciousness, against existential threats. And as we move out into the galaxy, we will need base camps, and a base camp on the scale of the galaxy is a habitable planet. And for more on the why and the historical and the ethical contexts, all of which are important, check out this asterisk essay with Robin Wordsworth, which was published 2 weeks ago. In that we do propose a few organizing principles for future research. Of course, we need to do more to show that life is absent on other worlds, especially Mars, before we consider making them habitable to life from Earth. Mars and the asteroid belt, which is the other emphasis of our asterisk essay, but I won't be talking much about the asteroid belt today. Although I'm very excited for future exploration, including the Emirates mission, which should be the first mission to land on the asteroid belt in the early 2030s. But they still have much to teach us about habitability and the origin of life on Earth, so we must be careful not to erase this archive until we've deciphered it. And our third, suggested guiding principle is not to consume any resources that might be vital to future generations. So this is especially relevant to think about water, ice on the moon, for example, which is very limited. And also to incorporate an off switch into any global experiments, so you can readily return to the pre-warm state if you decide to switch off terraforming. So yeah, I encourage you to check this out. It's open access. So it's been understood for over 50 years that there are 2 steps to allowing surface life on Mars. First, warm the planet up to 11 instances, which is relatively quick and easy on a civilizational scale, and then build up the oxygen level using photosynthesis. So I'll focus on the first step today. It's necessary, but not enough. And so any pioneer organism, the first to establish itself in the meltwater on a warm Mars, would have to handle multiple challenges, including high ultraviolet, perchlorates, and salt. I'm not going to talk about how those challenges can be overcome, except to say that it might require synthetic biology. We've learned a lot about Mars in the past 30 years. We have a much better sense of the organic matter content in soil and rock. It's about 0.5 kilogram per cubic meter, and the volatile and nutrient content of the soil. We know Mars was habitable in the past, so Mars's present sterile state can be viewed as corresponding to the largest known environmental catastrophe. And I like this example shown here, just because we see wave ripples from an ancient lake frozen in stone. And this was published in Curios Science Advances a couple of months ago. So you know that Mars was once habitable. We don't know for sure why it lost it. Another big change is our increasing capability to move material into space. So no particular imagination or hopefulness is needed to work through the economics of Starship, because it will likely develop similar to the Falcon rocket, which launches 3 times a week, meaning that the cost per launch will fall to the cost of propellant plus a small fraction of the cost of a single vehicle. That's about $10 million per flight, according to independent estimates. Now, Starships sent to Mars are realistically not coming back, at least initially. And so that's a $100 million vehicle cost per Mars flight. And they have to be refueled in Earth orbit. And so that roughly doubles the total cost. So you're looking about $200 million per Starship landing on Mars. And for that, you land about 100 tons of payload. So that's $2 million per ton. But right now, we spend about $1 billion per ton to land mass on Mars's surface, which means that in the next few years, barring unanticipated technological showstoppers, our humanity's ability to move material to Mars's surface is going to get easier by about 3 orders of magnitude. So this greatly increases the scope of things that we could do in space as a species. In today's talk, I'll first review what we know about Mars, so mostly aiming at the astrophysicists in the audience, then talk about how Mars's surface might be made habitable for life, just to sort of outline and deep dive into a technique that our team is working on, and then make the case for more research. So Mars once had river networks and lakes and a habitable climate, but lost that. So on the right is one of the river field sites, a river delta and lake deposits. Happily, Perseverance is actually driven off the screen at this point, which is magnificent and is sampling more ancient materials, hopefully to be returned to Earth sometime in the 2030s. And we see this all over the planet. It's not just Perseverance's location. But today, Mars's water ice is too cold for life. So temperature is the first barrier to establishing a second photosynthetic biosphere. But I would like to describe the modern climate a little bit. So this is a composite of Mars orbiter images. So it's a global view. And what you see is basically a desert planet with no liquid water anywhere. But water is in this image in the form of the polar caps, which are mostly water ice, about 2 million cubic kilometers, and in the form of water ice clouds, which form at high altitude over the equatorial region. The air is very thin. It's mostly carbon dioxide, but it only provides about 5 Kelvin of greenhouse warming. The problem is the water ice is in the wrong place. It's not in the warm, relatively warm equatorial regions. It's at high latitudes. It underlies about 1/3 of the surface. So this makes generating meltwater on Mars even harder because you've got to raise the temperature in relatively cold places with shallow buried water ice. This map is actually, the blue tones is actually a subjective confidence score. It is a synthesis of both geologic and gamma ray spectroscopy, neutron spectroscopy, craters excavating shallow buried water ice. It probably corresponds pretty closely to reality. The yellow line shows the moral predicted distribution. The models probably aren't wrong in that they sort of understate the distribution of the water ice. It's probably that the water ice, this equator of that is metastable and left over from a previous ice age. And if that sounds a little bit wishy-washy with a qualitative consistency score, here's more direct evidence. So fresh impacts seen from orbit splash out blocks of water ice from the shallow subsurface. And so those blocks out of equilibrium in the modern dry atmosphere only last a few months, but that's long enough to see those from orbit too. And so this confirms that Mars's present water inventory is at least enough to cover the planet 35 meters deep if evenly spread out. So there's lots of water still on Mars. In terms of the carbon dioxide inventory, Mars has about 7 millibars equivalent of carbon dioxide frozen as carbon dioxide ice, dry ice in the polar caps. And so warming Mars would sublimate enough carbon dioxide to at least double Mars's atmospheric pressure. Now, there are other reservoirs of carbon dioxide that would be released on warming as well. Most importantly, adsorbed carbon dioxide in the regolith, but those are less well quantified, with estimates ranging from as little as 1 millibar to as much as 100 millibar. And of course, Curiosity on cover of Science this week discovered large reservoirs of carbonates, but those aren't, you don't bake off the carbon dioxide until you get to very high temperatures, like hundreds of degrees Celsius. So those are out of commission, at least for short term. Curiosity has also shown us that Mars's soil is a harsh environment for most Earth microbes. There's one way of summarizing this is for any given, for any of the 5 or so stresses for microbial life in modern Mars soil, there's at least one Earth microbe that can cope with it. But as far as we know, there's no Earth microbe that can cope with all the stresses simultaneously. And so engineering life on Mars might well require synthetic biology. So in summary, Mars has the raw ingredients needed for life, including abundant water. But the causes of the habitable climates in Mars's past remains unknown. And so now I'll talk about how we might make Mars habitable, starting with warming. The amount of energy needed to warm Mars to habitable temperatures is roughly double what Mars's surface absorbs at the moment. And so that immediately means that darkening Mars, because it only subtracts from the reflected sunlight, is not going to be enough. So if I turned Mars's albedo down to 0, darker soot wouldn't be warm enough to melt. And so our basic levers are we can increase the incoming sunlight, or we can increase the greenhouse warming. So how to do that? You can add greenhouse gases. You can add dust in scare quotes, so engineered aerosol of some kind. You can bounce sunlight down to the surface using mirrors in orbit. You can add asteroids or comets to bring in volatiles. You can build a world house, which is basically a greenhouse that spans the planet. So with a roof that lets in sunlight but traps infrared. Or as suggested by the Harvard group, you can put aerogel tiles out on the surface, which due to their low thermal conductivity can trap both heat and infrared. I'm first going to say what the, I guess, state of the art was before we started working on it for global warming, which was a greenhouse gas approach. So work led by Chris McKay, but also Mimi Gerstel and Margarita Maranova in the early 2000s identified the ideal greenhouse gas mix, so the strongest warming you get for Mars. And it's a cocktail of gases, but they're all fluorine rich. And so fluorine is a necessary ingredient for this cocktail. And it was shown by European Space Agency study that in a 3D model, you do indeed get really strong warming with this cocktail of gases, and just 1 Pascal, so 1/600th of Mars's present atmospheric pressure can bump you up about 30 Kelvin. So 30 Kelvin is a sweet number because that means you start to get summertime melting. The annual average, global average temperature remains low, but you start to get summertime melting, and so that's a sort of threshold for, okay, this is useful and interesting. We have a planet that is at least partially habitable at this point. Sounds great. But the problem with this idea, and the reason why people didn't jump on it and start developing it further, is the fluorine demand. So 1 Pascal, correcting for the high mean molecular weight of the gases in this cocktail, corresponds to about 1 kilogram per square meter. Mars's surface area is 10 to the 14 meters squared, so you need 10 to the 14 kilograms of gas. It's mostly fluorine, so you need 10 to 14 kilograms of fluorine. Mars's soil has almost no fluorine. And so we don't know how to find fluorite on Mars from orbit. We can't prospect it from orbit because it doesn't have strong spectral features. And even if we did find it, we'd need a really big fluorite deposit. So there's no guarantee that this even works. And so that's where things kind of stood. This problem was recognized even by Carl Sagan before he died, and led Carl Sagan to basically write, yeah, this is going to be really hard. So our current research is on using engineered aerosols instead, so aerosols instead of gases. The basic idea is these particles are about 5,000 times more mass effective, so more warming per unit mass than the best available greenhouse gases. This is not optimized. This is basically the first thing we tried, and it works. So we are absolutely working on further improving and optimizing this. The particles are very light, so loosely very floaty. And so just like natural Mars does, you can release them close to the surface, and they get carried up to high altitude and spread globally by the winds. They float scatter sunlight, they trap infrared. And so this is how it actually works. So I'm going to start by talking you through the spectrum of natural dust aerosol. So natural dust aerosol on Mars cools the day side of Mars. The reason it does this is it has a high extinction cross-section in the solar band. So sunlight, and a relatively feeble extinction cross-section in the infrared. This is the total extinction cross-section. This is the scattering contribution to the extinction cross-section. So this is a log scale, so the albedo is like roughly 0.5. What this line is showing you is just whether the light is forward scattered or isotropically scattered. So natural Mars dust does forward scatter sunlight down to the surface, but overall it does cool the day side. Okay, so what's going on the right? The pink band is basically the full width of half maximum of Mars is black body emission at 210 Kelvin. And the reason the CO2 band is grayed out is because you don't really care about this gray band, because natural carbon dioxide greenhouse effect is doing a good job here of blocking the thermal from getting to space. What you need to block is this and this, the 10 micron, the 20 micron spectral windows. That's where Mars leaks energy to space, that's what you need to plug if you need to warm Mars. Okay, natural Mars does terrible job. Okay, this is the spectrum for the particles in our pilot study. So these are just basically half wavelength conductive dipoles. That's all it is. The actual calculation of the spectrum is a little bit involved because they're small enough that they become lossy, and so we had to use a finite difference time domain nanophotonic simulation, which is done by our Northwestern collaborators to get the spectrum. But I just wanted to show their behavior and contrast them to natural dust. So it's the same basic color scheme. So the solid line in the top panel corresponds to the extinction cross section. And you can see little sort of overtones here, nicely sort of just matches the 20 micron and 10 micron band of the sort of fundamental resonance, the 20 micron. The scattering cross section is again shown by the dotted line. So these are high albedo particles. They basically look like glitter in the air, towards vague glitter. And then the scattering asymmetry is just showing that you have isotropic scattering or nearly isotropic scattering of the thermophore, which is good. It means you're bouncing infrared back to the ground, which helps to warm us.
Edwin,
Yes.
That band, that absorption band, CO2 absorption,
Yes.
how much pressure broadening is it susceptible to? I assume this is at some pressure that's on Mars.
Yeah.
Is that
So.
very tiny.
So overall, we have 180 kilograms per meter squared of CO2 in Mars's atmosphere, and it provides only 5 Kelvin of warmth. Whereas a much smaller mass of CO2 in our atmosphere, about 4 kilograms per meter squared, provides a lot more than 5 Kelvin. So yes, and I'm not talking about water vapor feedback. I'm just talking about the direct CO2 effect. So yes, the fact that Mars's total atmospheric pressure is feeble reduces the per unit, which I think is what you're saying, right?
Yeah.
Good question. Other questions? Yeah.
If it's glittery, wouldn't it also tend to reflect light away, which is not optimal?
Correct. So the thermal infrared still wins there. So one way of seeing this is to look at the ratio of the extinction cross section in the bands that we care about to that in the visible, and it's a factor of dozens. Whereas the net cooling effect of natural dust is because the infrared opacity is about half that of the visible opacity. Okay, so this is the summertime temperature. So this is not a temperature that you would see at any one time in the Mars year. This is the warm time during the year. It's the average of 70 sols, so average over day and night, for just above the habitability threshold. So you can see the southern hemisphere gets warm before the northern hemisphere, and this is because the eccentricity of Mars's orbit combined with the fact that the longitude of perihelion is close to southern summer solstice. But the point is that the ground ice regions get above 0, and so you get some melting. But limitations of this pilot study, I mean, there are lots, but one of the most important is that we don't include water cycle feedbacks. So such high temperatures will cause a lot more water vapor in the atmosphere, which will tend to warm the planets up. It'll also cause more water ice clouds, which could either warm or cool, depending on details. And the ground ice will tend to migrate, trying to scurry towards cold locations. So we haven't calculated these effects yet. It's on the menu for 2025. It is a limitation to this pilot study. Another limitation is, in this calculation, we just painted the aerosols onto the atmosphere. The distribution of the painted on aerosols was motivated by the observed distribution of natural Mars dust. But to warm Mars, the particles have to disperse globally. And as the aerosols warm the atmosphere locally, they'll feed back on the winds. So these relative dynamical feedbacks matter both locally and globally. Because you have relative dynamical feedbacks at the release point, and you also have global gradients in the aerosol abundance, which will feed back on the winds. This has also been studied in the context of stratospheric aerosol injection geoengineering for Earth, although with more of a focus on the global feedbacks. And so we asked, how high are the aerosols lofted with plume tracking? How widely do they disperse? Do they drive local weather at the release point? How long until steady state? And does release location matter? So I'm now going to summarize the results from this study, which was led by Mark, who's in the audience and is on the archive. And we aren't the first people to study plume tracking for Mars. So it's been studied in the context of relatively passive methane plumes. And we used the Muswell GCM. Again, a major restriction is we used a dry simulation with no water cycle. And we had near surface release of the particles, which in the context of these simulations means about 10 meters above the surface, or within a grid box that extends 10 meters above the surface. So what you see here is just a movie showing the particle release. It's doing some kind of stop-start thing, which is not real. And the overall rotation, that's the diurnal tide sweeping through. And the size of the mesh is about 1,000 kilometers top to bottom. And the color is the nano-aeronautical depth, so they're being stirred into the background atmosphere. In this simulation, we considered new and improved particle types, of which the most important is graphene disks. So graphene is a two-dimensional material. It's made of carbon. And because it's only a single atom thick, you get a lot of radiative forcing per unit mass. Graphene is actually translucently visible, but graphene disks have been shown experimentally to resonate in the thermal infrared. And the reason for this is kind of cute. So we normally think of electrons as moving incredibly sluggishly through conductors, like hundreds of meters per second of that. But in graphene, that's not true. The electrons are moving at thousands of kilometers per second, which means that you actually resonate, the electrons are sloshing from one side to the other of the graphene disk, when the graphene disk is about 1% of the size of the wavelength of light with which it's resonating. So tiny graphene disks, a couple hundred nanometers, resonate with thermal infrared. The main results from the plume tracking is that relatively active feedbacks help boost the aerosol to high altitude where it can disperse globally. So what I'm showing you here is results 30 sols after we switch on the aerosol release. The actual release location turns out not to matter that much, but for what it's worth, this is a 40-degree north side. So with radiative feedbacks, the plume goes up to about 1 scale height, whereas without plume feedbacks, without radiative feedbacks, the plume goes half as high. And here is the day-night cycle in the same basic idea. So I expected that the particles that we released during the simulated night would be wasted and would just fall onto the ground. That turns out not to be the case. They just kind of like hang out close to the ground and wait for the daytime when they're ventilated to high altitude and affected depth. And so this just shows that the planetary boundary layer is indeed thickened by the plume. So these are 3 different cross sections through the plume. So this is at the release point. This is 1 grid cell downwind, and this is about 100 kilometers downwind. And so this is just showing the particles being infected and mixed into the background. These are computationally intensive runs. We couldn't do this for the many simulated years. And so I'm now going to switch to showing you lower spatial resolution 60 by 48 by 40 X, Y, Z runs that were done to find global steady state. Okay, so this is the steady state icon. And the other 3 panels are 3 steps in achieving that steady state outcome. So the main point is that the particles are pretty well mixed in steady state. So the particles take only half a year or so to be well mixed. And at steady state, the gradient in particle abundance is pretty small. So this is 0.24 optical depth. This is 0.26 optical depth. So we're looking at 10 or 20% gradients in particle optical depth, except right at the release. And this makes sense because, again, the particles are very floaty. So the gravitational settling rate is negligible, and most of the removal of these particles is through diffusion out of the boundary layer very close to the surface. Okay. And who likes atmospheric dynamics? Wow. Okay. All right. I will. Okay. Not everyone loves them. That's right. Okay. Yes.
Sorry, one follow-up on the previous slide.
yeah.
What happens when they settle onto the surface? Do they like adhere there, or can they be lofted again later by another wind event?
We assume that it's perfectly absorbing, and I think that's probably true. They're so small they just kind of like fall in between. Now, there is an exception to that, which is if they settle onto the CO2 cap, then they're probably relofted by the sublimation rate. So in that sense, it's conservative.
So, Edwin, what do you include in these simulations? Do you have charge effects, for example?
No, these are very simple. So the only aerosol that's like actually tracked to the model is the particles. So we don't have interactions between the dust, the natural dust cycle, and the engineered aerosol. We do have natural dust in as a sort of radiative forcing, but that's just from the Mars Climate Database, like a sort of stylized version of the natural dust cycle.
But my question was, could these particles get charged? Would that affect their distribution? For natural Mars dust, charging matters actually for the biggest particles. For these particles, we probably would want to charge them initially. No, so they repel each other because clumping or agglomeration is the enemy here, right? And this is so common a problem in like aerosol research that you just buy coronal discharge chargers. So even for just studying aerosols, you need to charge them up in order to just separate them enough. So when they emerge, you want to charge them so they repel each other. What the steady state charge is, we haven't calculated. Mars's Hadley cell, as shown in a Nature paper by Mark from 2002, is asymmetric due to topography. And so this is just the southern summer Hadley cell. But the global warming, even though it's roughly symmetric in latitude, leads to a intensification in the Hadley cell in both seasons, which helps to stir and mix the particles. And so on a global scale, the radiative dynamical feedback is favoring warming by favoring mixing. But none of this would matter if we couldn't make these particles. So what I'm showing you here is a sort of rigorous metric for making particles. So on the x-axis is how much energy you need to put in steady state to keep making these particles because they're settling out. And on the y-axis is how much global warming you get. For feedstock production, this caveat just means we're considering only the first step in making the particles, which is taking natural material and converting it into carbon. So carbon dioxide electrolysis, which was demonstrated by Moxie on the Perseverance rover, or taking soil and using metal regolith electrolysis, which has not been demonstrated in space, but a lot of companies are planning to do it on the moon to extract metal in the case of aluminum particles. So the feedstock production means I'm ignoring the energy cost of subsequent steps in making the particles. And that's probably about right. This first step is the most energetically intensive. Okay, so the numbers next to the lines, the colored numbers correspond to the production rate in liters per second of particles. So 1 liter per second is roughly one big garden sprinkler. So maybe not the one that you use in your own garden, but a sprinkler that you might see, out here on campus. Okay, so this is very encouraging because the energy inputs are not that large, given that we're talking about a whole planet's climate. But there are two big caveats associated with this plot. The first, as already alluded to by Professor Malhotra, is we haven't included all the climate feedbacks yet. The climate feedbacks could move these lines up or down. The second caveat is particle production protocols have not actually been established for these particles. They can be made in the lab, to be clear.
but the quantities that are made in the lab are relatively small. And so we don't know how much extra complexity is involved in getting from feedstock to the particles. And so that's another big caveat with that one. So where are we now? Well, taking the graphene as an example. Oh, sorry, I didn't completely explain this. So the dashed line versus the solid line, that's two different release sites. So the solid line is an equatorial site and the dashed line is a mid-latitude site. So there's a few Kelvin advantage to going to an equatorial site. So where are we right now? So Moxie demonstrated carbon dioxide electrolysis. From Moxie's point of view, making carbon is actually bad. It didn't set the voltage too high because they hit what they call the coking threshold. But a spin-out company called Noon Energy, which is from the Moxie team, is very much using this same method to make soot as an energy storage technique. Store the soot, recombine it with oxygen when you want the energy back. And so this is a plausible first step in making lots of graphene. You can make the graphene directly by carbon monoxide disproportionation by the Boudouard reaction. So this is a plausible first step in graphene. But the scale is minute compared to what we need. And so this is just the first step on a long road. It's a road we'll have to travel down though, because if we want to fly spacecraft back from Mars to Earth, I personally don't want a one-way ticket to Mars. Then does anyone want a one-way ticket to Mars? Wow. Okay. All right. Well, you are the pioneers. Then we'll need to make thousands of tons of oxygen on Mars by techniques like this in order to replenish the propellant tanks of spacecraft. That is the scale we're at on Earth right now. So right now on Earth, we can make thousands of tons of graphene per year, although not using this method. And so that would have to be scaled up to tens or hundreds of thousands of tons per year to get global warming by the method I've just described. So how quick would it be? Basically very quick. Once you've got the infrastructure in place, Mars has very little thermal inertia. And so the temperature response is immediate. There's no ocean to provide thermal lag. But of course, you wouldn't actually just switch on a Mars warming system with no experiments. You would do sort of subscale experiments, see what the climate feedbacks actually look like, rather than just in a computer model, and then make a decision to either, okay, this isn't working or isn't doing what we expect it to, turn off, and then Mars will return to the pre-warm state very quickly within a year or two, or proceed to full warming. And so here on this graph, the blue disk is just when you start to get summertime melting. This is an entirely new approach to warming Mars. And we're only basically 2 papers into what will be a lengthy research program. So I don't want to leave you with the sense that we're sure that this will work. So possible showstoppers include graphene functionalization, because you don't want the graphene plates to stick to each other, for example. And related to that, preventing agglomeration. And I already mentioned modeling water cycle feedbacks. If the ground ice just scurries away and sits on top of Olympus Mons, worst case, then you would need about twice as much warming to actually get meltwater than if the ground ice stays in place. So these are big challenges. And precisely for that reason, that we don't know for sure that this will work, it's worth considering alternative ways to warm Mars. So I now want to briefly touch on a few alternatives suggested by others. So one is starts with Phobos, city-sized potato moon in low Mars orbit, Dan Fabrici and Ben Bromley have shown that you can warm Mars through dust launched from Phobos. So this is just sort of unguided dust. And so again, this GIF isn't doing what I hoped it would do, but what you're seeing here is Mars's view from the sun. Phobos and Deimos's orbit are gray. They're precessing because you're looking down the Sun-Mars line. And the yellow is just sort of rings that are proxies for shells around Mars. And the main point of this one is that the time averaged effect is to scatter a lot more sunlight down to the surface than you block, leading to Mars warming. And I'm pretty optimistic about this. We've got seed funding from UChicago. Dan Fabrici is the lead to look at this more. The reason I'm optimistic about this is because we are not even including the thermoinfrared blocking effect yet, which will further warm Mars. Another option is using solar sails in Earth orbit that fly themselves to Mars and then bounce sunlight down to Mars's surface. And so what's nice about this is it buys you a factor of 10 because you don't have to do the trans-Mars injection. And so even though the solar sails have more mass per unit area than the aerosols, we could loosely start this tomorrow, although they would be pretty inefficient because our solar panels aren't great, without needing the complicated tech stack of doing in-situ resource utilization scaling on the Mars surface. So, that's another possible warming method. And of course, these methods could work together. This method is especially good for warming Mars's poles. The engineered aerosols that do a better job of warming Mars's equator. And then, as previously suggested by Robin Wordsworth, Laura Kerber, and others, you can just ship in aerogel and tile the surface next to your landing site, creating a sort of local garden. I mean, garden makes it sound like they're going to be roses and stuff. Like flowering plants can't survive on Mars because the oxygen level is so low. Plants require oxygen. So this is more like a garden where you can like get the ingredients of tofu. And so the problem with this method is it doesn't scale to the planet. One way it might scale to the planet is if you come up with some way of making aerogel using synthetic biology, which no one has done yet, but that would make this method scale. None of the ideas I'm talking about give an atmosphere that we can breathe. We don't even know that that's possible. What we do know is that if you get a photosynthetic biosphere going, the oxygen level will gradually rise. And there's no reason to think that the oxygen level wouldn't eventually enable flowering plants and relatively complex but non-animal life. But I don't want to suggest that oxygen buildup is something that we know will happen to human breathable levels. We do know that oxygen buildup will be slow. So I just showed you a graph where temperature shoots up in a couple of years. Oxygen is not going to do that. The energy for making the oxygen is coming from sunlight, which is a fundamental upper limit on how quickly you can raise the oxygen level. And with realistic efficiencies, it would take centuries at least to build up oxygen level on Mars to levels we can breathe. I think it's important to say this because Mars is not really a backup planet. For the foreseeable future, almost everyone's going to live here, making Mars a second Earth is a dream, but it's a dream that's several centuries out. The shorter-term goal is making a green Mars, one that can support a photosynthetic biosphere, but that's not one that's a good home for us in large numbers. Yeah.
If you're converting this atmospheric CO2 to O2, are you losing the greenhouse effect? Is that going to be self-inhibiting?
No, the greenhouse effect of the CO2 is pretty feeble. In contrast to like the early ideas of Sagan and McKay, which assumed over-optimistically a large reservoir of carbon dioxide ice in the South Polar Cap, the warm states I'm showing, almost all the greenhouse warming is supplied by the engineered aerosol, not by natural CO2. Does that make sense? Yeah, okay. But there are other reasons why you don't want CO2 to be that high, because if you eventually want the atmosphere to be breathable, humans can't cope with 10 millibars or more of CO2. Who's got the CO2 monitor in their office or their bedroom? Oh yeah, I recommend it. It was terrifying when I first installed it. Oh, that's fine. That's why I'm not productive. Okay. So warming Mars is a necessary but insufficient step to allowing an oxygen-producing photosynthetic biosphere. The classical approach to warming, which I just sort of adumbrated and answered to super, it doesn't work because there isn't enough CO2 ice in the South Polar Cap. But there are other more mass-efficient ways to warm Mars by or more. So as Carl Sagan said, advocates of terraforming must first become
advocates of scientific exploration of other worlds. We've learned a lot about Mars in the last 30 years, but we need to learn a lot more before making any choices or commitments about Mars's future. And I think there's a lot of overlap with existing community priorities. We know that Mars has enough water for seas, but we don't know if Mars has enough water for oceans. We need to check for deep water bodies. And I think active electromagnetic sounding is a sweet technique for doing that. If they exist, we must check them for life, which will involve drilling kilometers down through the rocks of Mars. And a study of that life could have great benefits that warrant robust protections for its habitat. So all of that needs to happen before we introduce our own form of Earth-derived life into Mars. So I showed you a qualitative map of water ice distribution and said, well, we are not sure if we can trust the same 1 pixel, but there are at least a few places where it's been spot checked by impacts and it looks good. That's not good enough. If we're going to do large-scale in situ resource utilization, we need to know exactly where the water ice is, how deep it is, how thick it is, and so on. And the International Mars Ice Map mission, which is a proposed high-resolution radar, is one way to get close to that. So these are existing community priorities. This is just fresh motivation for those existing community priorities. And I think you can go on to, we need to have a better understanding of Mars's modern weather and climate. And you sort of get that for free with any terraforming precursor mission, which has to carry a good weather station. And so that's another area for that. So this is what we're doing currently. So we're basically trying to improve our particle design. We're considering a wide range of particle types and screening them using, actually right now we're screening them with the 1D model, but once we've got good candidates for that, we'll put them, just that. Put them into a 3D model. And basically doing what was done for gases 20 years ago, which is just optimize the relative forcing. But you can't rely on experiments alone. Eventually, you'll have to do small-scale local experiments on Mars, I think. Looking ahead, the emergence of photosynthetic biosphere on Mars will be a bit like descending a mountain on Earth. So this idea was previously pointed out. So first you have really simple forms of life like snow algae and so on, and then more complicated bryophytes and lichen, and eventually flowering plants. So with that, I'll wrap up. So new options for warming Mars have emerged. New Mars transport vehicles increase the mass planning hurry for. It's not just Starship, of course, it's also New Glenn, relativity and impulse space to proposing a Mars-landed commercial Mars payload services are very much on the horizon with study contracts issued by NASA, mostly for Mars orbit, with a vision of commercial Mars surface payloads. And we've learned a lot about the basic science of Mars as well. And so with that, I'll just leave you with my conclusion slide and happy to take any questions.
Very much. Questions from the room? I see a question back there.
Yeah, so it's probably too early to ask this question, but nonetheless, you have 3 different alternatives for doing the warming of the planet. What's the relative cost of them, and what's the absolute cost of them in terms of the number of Apollo project equivalents or something?
Well, I would kind of turn it around and say this isn't going to happen unless the answer is of order unity. But I don't have a cost estimate that I can defend. Of course, I have a spreadsheet which has a dollar number in a cell in the spreadsheet, right? But it's not like a mature number that is worth sharing. But yeah, I mean, certainly the idea is to push things towards like one Apollo project together. Yeah.
But are all 3 of them equally costly, or is one cheaper?
At the 2024 Mars workshop in Pasadena, we had this exercise, and we couldn't convince ourselves that one was a clear winner. Now,
Okay.
it's definitely true. The aerogel method, you can start really small, right? So the aerogel method is, in a sense, like you could start doing that on the first Mars landing. So in that sense, it's cheapest, but it doesn't scale to large sizes unless you can biologically manufacture the aerogel, which we cannot do yet.
I would have guessed that the tiling was the most expensive, but I don't know. That's what I'm asking. So,
Oh yeah, sure. Sorry, when I say aerogel, I mean the tile.
oh, you do?
The aerogel tiles are about 2.5 centimeters thick, which is thick enough to provide thermal insulation for the warm soil. And this has been demonstrated in a vacuum chamber by Robin.
Question over here.
We thought about the potential to sequence aerosols, as you showed the climate responds rapidly. So you're gonna be chasing the black body, and you're gonna be chasing water vapor bands that are appearing in the spectrum. And so you could kind of tune your aerosols to respond to that.
Totally, check out our archive post. So we have the 250 nanometer graphene, we have the 1,000 nanometer graphene. As you would expect, the 1,000 nanometer graphene is better for warming the higher latitudes. The 250 nanometer graphene that tends to already warm places. So yeah, in principle, you could dial that in as the platforms. Absolutely, yes.
Yeah, all life requires nitrogen. And as far as I know, nitrogen is in short supply on Mars. There might be a bit in the atmosphere. So where you get the nitrogen from, and if you get it from the atmosphere, you would have to fix it into a form suitable for life. Right? Can you address that?
Yeah, so there's 3 kilograms per meter squared of nitrogen, in Mars's atmosphere. And there's about 100 parts per million by weight of nitrates and nitrites in the soil. So that's what you got to start to work with. And then the details of the geomicrobiology of how you fix that nitrogen outside my expertise. But that's what you've got to start to work with. 3 kilograms per meter squared in the atmosphere and about 100 parts per million by weight in the soil.
I actually had a question about the soil nitrogen.
Yeah.
How firm is it that that's actually nitrate versus peroxynitrate, something like that?
My reference is basically Stern 2015 PNAS, and they say nitrate.
Yeah, they found oxidized nitrogen, but I didn't see that they were ruling between nitrate versus the peroxy versions of those species.
Yep. So there's been subsequent work, or
no? It's just like I thought that was a simplification of the paper, and I was wondering if the community thought further about that or not, like ruling between those possibilities.
I think that sounds like a good area to do some research. Yep.
We could talk a little bit about the geopolitical aspect of all of this, right? No one owns Mars.
Yeah.
How do you get the world on board with one idea, or what is the thought process there?
Well, do the science first. I mean, we have multiple examples of the world pulling together and agreeing on rules for previously empty spaces. The Antarctic Treaty is one. The Outer Space Treaty itself is another. The International Seabed Authority is a third. Every country, I think literally every country in the United States has signed up to the United Nations Convention on the Law of the Sea, which includes agreements on mining in the deep sea. Can we pull together again? I hope so. But at a minimum, you need a consensus among all spacefaring nations, similar to the Antarctic Treaty, which isn't signed by everyone, but is signed by everyone who is like in Antarctica. But the digital mechanism, I have not.
Yeah, so you'd mentioned like toward the beginning of the talk, I think that like one of the principles of like the guiding this research was having sort of like an off switch for wanting to revert something to the pre-warmed state. Forgive me if like you did mention this and I missed it, but do these 3 methods, like, do they all have a plan, like theoretically, for that off switch, or is that something that's still being discussed?
Well, the method we're working on, aerosols, is in many ways the messiest of the 3, right? Because with mirrors in space that just destructively enter. With tiles, okay, I mean,
they just stay there, but they're not covering a huge percentage of the surface. So what that means is that the particles have to be engineered to individually degrade in
Interesting.
water.
Yeah.
And so the easiest way to do this with metal rods is just to make them so thin that they oxidize and break into tiny fragments. You can also functionalize them to make them delicious, which in the context of Terraform Mars, the graphene disk could be compost, right?
Yeah.
And there are other methods as well. One is if you have a rod or a disc or a ribbon, you can engineer spaces into it that are so thin that they don't affect the radiation properties, a few nanometers, say, but that's still like dozens of atoms, right? And then they just fragment when they contact liquid water because you have soluble spaces down there. So, for example,
Yeah, so these examples of life that are thought to exist at these different stages, is the idea that these would be introduced from Earth life, or they have to independently have biogenesis and evolve?
Well, I mean, if there's life on Mars, then most of this talk goes out the window, right? Whether or not you think that ultimately some kind of symbiosis or coexistence is a good idea, the first thing you would do is study Mars life in isolation until we've got all the scientific value out of it, which would take like a century. The idea of like life spontaneously emerging from the newly habitable conditions is not what I seriously. It's not what I thought about. But I think this is a bit of a jump, but like Titan is a more natural origin of life experiment because every time a comet hits Titan, it creates a liquid water melt pool in the ice crust, which is irrigated with organic molecules. Great example of Darwin's Warm-Riddle Pond. Then that melt pool freezes over and goes down to 100 Kelvin, meaning that the prebiotic experiment is perfectly preserved for us to explore. So I think to do that experiment, I would be more motivated to go to Titan and drill into some impact craters rather than to warm myself and wait 1,000 years or 10,000 years or longer than the age of the universe.
So, okay, so since you don't imagine that necessarily, when you're saying this life would, in these papers, this idea is the life originally comes from Earth and is introduced?
So in the papers I've been involved in, we haven't even got that far. We're just asking about what you need to do to get melt water.
Okay, I was just asking about the pictures of life that are.
Oh yeah. So in the
where they came from.
Yeah. So there the assumption is it's brought from Earth, yes, but possibly with some synthetic biology, especially for the pioneer species.
I was wondering about the feasibility of melting the poles versus the mid latitudes, because yes, at the mid latitudes it's, I don't know, 50 Kelvin warmer, but you also have debris cover layer that is protecting the ice, right? So would be easier to, even with that layer, melt the ice from the mid latitudes, because what we have seen on Earth is like actually debris covered glaciers are very resilient to global warming because they are protected, right? So I was wondering if even with that layer, it's still more feasible just to melt the cover ice than the exposed ice at the poles.
Yeah, so we see debris covered glaciers as low as like 30 degrees latitude on Mars. They're protected by many meters of debris cover. But from gamma ray spectroscopy and neutron spectroscopy, you can actually constrain the thickness of the cover layer. And there are other geologic methods for constraining the thickness of the cover layer. And basically the layer is thin enough that if you keep the high temperatures for 70 sols, you'll start to get liquid water. One place where we know that's true is the Phoenix landing site, where the debris cover is only 6 centimeters thick.
I think I saw a question from Devin.
Yes, I'm wondering if in your methods, have you considered is there any potential for any positive, potentially destabilizing feedback loops, or is something analogous to like some sort of carbonate silicate cycle on Earth expected to kick in once the heating happens?
So I think kind of like weathering feedbacks are going to be so sluggish compared to, human inputs that they're not going to affect the carbon dioxide level much. The destabilizing feedback loops, I don't think so. I mean, that would make things easy. That was the hope. That was Carl Sagan's dream in the 70s. But you just need more carbon dioxide, volatilizable carbon dioxide on Mars than actually exists. But there are definitely geochemical issues that are sort of downstream of this that we have to worry about, which we haven't thought through thoroughly. And the most basic is, vineyards on Earth, very fertile places on Earth, that's fresh volcanic ash, right? Or recent volcanic ash. We can't rely on that kind of soil refreshing on Mars. It's a tectonically quiescent planet with slow resurfacing. And that could, mean that nutrients, which was brought up by someone possibly secret, are going to be, a big worry, as they are on Earth, but even more so on Mars. So that's the geochemical cycle I worry about. It's soil nutrients on 1,000-year timescales. Yeah, that's actually interesting.
I'm going to take the privilege of the last question because we still have the time step symposium that's going on outside. You're of course welcome to ask Edwin more questions later. But just one final question I wanted to ask is about the principle of irreversibility. If you heat up the planet a bunch and you get a bunch of water vapor in the atmosphere, it's a thin atmosphere, so your diffusion of limited escape is still going to be relatively efficient. Are you going to irreversibly lose a large amount of hydrogen such that if you shut down the experiment, you couldn't theoretically do it again, or is that not a concern?
That's still really, really slow. I mean, 10,000 years is like a reasonable thing for the foreseeable future, right? No, it's not going to matter.
Well, let's thank Edwin again for coming by.